A fictitious force, also known as inertial force, is an apparent force that acts due to a non-inertial frame of reference. Non-inertial frames are frames which are accelerating relative to you. An example of this would be the frame of reference inside a car accelerating past you. The other type of reference frame is the inertial frame. In this case, the frame is traveling at the same velocity relative to you, such as the frame of reference of your friend sitting on the opposite end from you on the bus. The two frames we will be dealing with in this video are the ground frame, which is the frame of reference for us on the ground, and the rotating frame, which is a non-inertial frame of reference inside the rotating objects, such as in the roundabout.
To start with, we will be deriving the equation linking the acceleration in the ground frame and the rotating frame, where we regard the true acceleration to be the acceleration as measured from the ground frame. We have a position vector r. A small change in r is equal to the change in angle times the position vector, since it's circular motion. Since we want our result to also be a vector, we cross it with a unit vector along the axis of rotation n hat. We can now define d phi n hat as d theta, and get that dr equals d theta cross r. We can also define the angular velocity vector omega as the angular speed times the unit vector n hat, such that d theta equals omega dt. Substituting this for d theta above gives dr equals omega dt cross r. Since dt is a scalar, we can divide through by it to give dr by dt equals omega cross r. Splitting dr up into its components, we realize that we can write each one in the same form as above, as they are independent. Expressing the velocity vector v in terms of the base vectors of the inertial frame and the base vectors of the rotating frame with the apparent vector in the rotating frame allows us to write down the acceleration, dv by dt. Since both v and the basis vectors depend on t, we use the product rule to get that this is equal to. We can simplify this by realizing that the first part is perceived acceleration. Applying the identity dr by dt is omega cross r to the second part gives us omega cross v dashed x I hat dashed plus v dashed y j hat dashed plus v dashed z k hat dashed. We already know that this is just the vector v in the rotating frame, so dv by dt equals dv by dt apparent plus omega cross v. Doing the same for the position vector gives dr by dt is dr by dt apparent plus omega cross r, or v true equals v apparent plus omega cross r. Substituting this for v in the equation above yields dv true by dt equals dv apparent by dt apparent plus omega cross v apparent plus omega cross v apparent plus omega cross r. Simplifying this gives us the formula linking acceleration in the inertial and the rotating frame. A true equals a apparent plus 2 omega cross v apparent plus omega cross r.
Now we put a free coin in near to the center of the turntable and start to rotate the table with an increasing angular velocity. Once the speed of the turntable is quick enough to overcome the friction between the coin and the table, you will see that the coin flies away from the turntable. There must be a force against the friction that gives the coin an acceleration away from the center of the table. This apparent force is what we call the centrifugal force. Then we connect the coin with a string to the center of the table, as you can see in the video. Before we spin the table, you can see that the string is loose, but now the string is taut. This tells us at this moment the centrifugal force has the same magnitude as tension but in the opposite direction. Using the equation we derived earlier, we can equate our experiment conditions into the equation. From the video, we can see that the coin is stationary in the R-frame, so both the acceleration and the velocity of the coin in the R-frame are obviously zero. We can then rearrange the equation and get. From here, we multiply both sides by the mass to get the equation for the centripetal force. Since we know that the centrifugal force is equal and opposite to the centripetal force, we can just add a minus sign to the right-hand side of the equation above, and this gives us the equation for the centrifugal force.
Now we're going to show you another phenomena you can observe when you're in an R-frame. As you can see in the simple experiment inside a roundabout, the ball moves in a curved path in the R-frame. This curved motion is known as the Coriolis effect. The effect will only occur if an object is moving relative to the R-frame, and the force that causes the curvature of the ball is known as the Coriolis force. However, when you're looking at us from the G-frame, the ball is moving in a straight line along the trajectory and a constant velocity. Then, how can we determine the force in the G-frame? Using the equation we derived earlier, in our example, the velocity of the ball in the R frame is constant, so there is no acceleration parallel to the direction of motion in both frames. Therefore, we can make this term 0. After rearranging the remaining terms in the equation, you will get this. As you can see, you will get two negative terms. The second term was mentioned to be the acceleration caused by the centrifugal force previously. This leaves us with the first term, which is the negative acceleration caused by the Coriolis force. After multiplying both sides with mass, we will get a formula for the Coriolis force.